Okay, so here what we're going to do is just look at the four different models, basically, of what an atom is and how it came to be. So, Sierra, since this is yours, you don't actually have to do these warm-up questions, but this is what I had them do. We're going to take a look at what you think the atom is and compare that to the models that we're going to go through and see where you stand. So the first thing we need to do is look at some ancient history. Two ancient Greeks. Democritus was actually the first guy to come up with the name and the idea of an atom. The idea was that matter, you couldn't break it down to infinitely small parts. There had to be a level at which you cannot divide it anymore. All right, so you take a big rock like this, you break it down into little particles, but there was a point. And the point at which you couldn't break it down anymore, so you couldn't split it, that was called an atom, which means indivisible. Aristotle took this idea and kind of changed it a little bit, where he's saying that now matter isn't just atoms of rocks or atoms of chairs or atoms of air, or atoms of a fish or atoms of a human. What they are is actually four different types of atoms or elements, and his elements were water, fire, earth, and air. And any kind of mixture of these could get you different things. So you take these four elements, mix them up, and you can get anything that you want. Those are the two early ideas. All right. Now, more scientifically, though, John Dalton in the 1800s was the first guy to really come up with a model of the atom that was based on experimentation, not just pure reasoning and speculation like those guys had. So here's what Dalton thought of the atom. A couple things that you want to know about him. First, he thought that all matter was made out of atoms, not much different than the other guys. That atoms of an element, are identical. So all hydrogen atoms are the same, basically. All helium atoms are the same. And each element, though, has different atoms than other ones. So hydrogen atoms are not like helium atoms. Or oxygen atoms are different than those. And he also said that just like Aristotle thought, you could mix different elements up to get different compounds. Like water is H2O. And if you want water, you have to have two hydrogens for every oxygen. So there's a specific ratio that they have to mix up and combine into to get certain things. And that happens when atoms or elements react. Atoms rearrange themselves in those chemical reactions. And if you were to actually sketch out, which is very important, what his model looked like, it's called the billiard ball model. And it's because atoms are these solid, indivisible bits and pieces. So it's just like a billiard ball. You cannot break a billiard ball into different pieces. That was his idea with the atom. That there was nothing beyond the atom, anything smaller. It was just a spherical ball, billiard ball, that could not be divided. And different elements had different types of billiard balls, but they'd all be indivisible. Now, we know that nowadays that there's protons, neutrons, and electrons. To figure out how we came about knowing that they're subatomic particles like an electron, the first step was something called a cathode ray tube. And a cathode ray tube kind of looks like this. I think this is like the old TVs, the CRT TVs, they're really big. They actually shoot a beam of electrons at a screen. They're not like your flat panels LCDs today, but it's kind of like this. And let me show you a little video to explain. All right, so you've got a disc of metal here and a disc of metal here, and then when you put a really high voltage across, you get this beam. Now, what's interesting about it is when you bring a magnet near it. You can see this beam isn't just light, but it's actually a particle that has magnetic properties. It's repelled by one side of a magnet, and when you flip it around, this beam actually is attracted to the other side. And if this is a positive side, that means it's attracted to the positives and repelled by the other side, which means it's negative. So since that beam was attracted to the positives and repelled by the negative side of the magnets or an electrical field, he actually discovered the electron, right, which he determined was exceptionally small mass, an exceptionally small size. In fact, it was smaller than an atom, so he knew it was part of it. He also knew it was negatively charged, and it was fundamental. All atoms, regardless of the kind that he had in those little disks, all had electrons. And this is known as the Thomson model, or the plum pudding model. And the reason for this is because he discovered an electron, and he figured since an atom is neutral that there has to be a positive, but he couldn't ever really find it. So he thought that it was a negative electron in a positive framework. So what does this look like? Think of a chocolate chip cookie. Chocolate chip cookie has those chocolate chips which you could pluck out. Those are like your electrons. And the dough is what they're embedded in. If you think of plum pudding, okay, plum pudding is there plums inside of a pudding. And you can easily pluck out the pudding, or the plums, but the pudding itself doesn't come flying out. That's the way that he described the atom. So it's kind of like the billiard ball, but now there are bits and pieces inside of it. All right, next one. Ernest Rutherford. Okay, this is going to be the Rutherford model. This is probably most similar to what you guys think about when you talk about an atom. So let me explain his experiment first. All right, he shot positively charged particles called alpha particles at gold foil. All right. Now, the way you make these alpha particles is through something that's radioactive. So you have this lead block, radioactive substance that was shooting out alpha particles at gold foil here. Now, it's really, really thin, just a few atoms thick, and the alpha particles, which are invisible, right, would hopefully go through, what he thought at least, would go through these atoms, hit the phosphorescent stuff, so that when it goes through, it actually would glow. All right, and he was actually trying to measure the size of these atoms, and he thought it would go straight through, because if those electrons in the Dalton model were evenly spaced, then there wouldn't be attracted or repelled in any specific direction. It'd just go flying right through. But what he found when he had, basically, it's more like a circular disc around this gold foil, is that most of it did go right on through where he expected. But a small portion actually was deflected. And even a smaller section actually got shot backwards, which is a little bit odd for him. And the way he described what was going on here was that the alpha particles, for the most part, went right on through the atom. The small portion were deflected by some massive positively charged portion of the atom that was previously undescribed. And if it hit it straight on, it reflected back. Now, a very, very, very small percentage was deflected back. So what he then described was a new model where atoms are mostly empty space. There's a massive positive nucleus, right, called the proton. He knew about protons. He didn't know about neutrons. He discovered protons, basically. That the negative electrons orbit around this positive nucleus. And the electrons, here's an important detail, could orbit pretty much any distance. So this is kind of like a solar system model, that you could really have planets at any distance from the sun, and it'd be fine. It would, you could have an asteroid in between Mars and Jupiter, or you could have something going in between other planets, and it's not a big deal. The reason why I harp on that is because that is the main difference between the Rutherford model and something called the Bohr model. Now, the Bohr model is very, very similar, but what his difference was that electrons orbit the nucleus in shells or specific energy levels. Now, each energy level or shell has to be a given distance, and you cannot be in between. The way that he came up with this was actually looking at something called the spectrum. Now, let me kind of just show you the model first here. So, if an electron going around the nucleus either gets hit by another electron or absorbs a certain amount of light, it actually bumps up to another energy level. And when it jumps down, it actually can release that energy in the form of light. What we see, though, when we take that light, and if you've ever seen a rainbow, you've seen a spectrum, but if you do it in a specific way, with low density gases that are heated really high, you can actually split it, and it doesn't form a rainbow, but it actually gives specific lines of colors. And those lines of colors give off specific amounts of energy. So let me show you what he thought was going on. So we have the positive nucleus, electron, and specific orbits. Now, depending on how much energy I give this electron, for example, if I give it this amount of energy, oops, let's try another one. Try that one. It will actually jump up to that certain energy level. And then it falls back down, it re-emits it. If I give it a different amount of energy, though, say a certain amount of energy that would only put it at this distance, it doesn't absorb it. It goes right on through because it has to have enough energy to jump up to this next step, not in between the steps, right? But from this step to this step or another one. So if I give it a little bit more energy from here to here, it'll absorb it and shoot it out. But if I just pick a random amount of energy and shoot it at this, whoops, you could lose it if it's enough to jump out. But if it's not enough to jump it up to the next one, at least it doesn't go. So the main difference here that we really need to think about from the Bohr model to the last one with Rutherford was that Rutherford could have an electron at any distance from the nucleus, where Rutherford had specific shells or energy levels that it has to meet. That's the main difference. Those are the main models that we're going to use and discuss. So there's your first video. Hope it goes well. Make sure you take good notes on it.